session, and we're going to talk about the exam. So my plan is there's a practice exam that's been posted already. I'll get the key up soon, also the homeworks. My plan is to have the exam be open starting tomorrow morning, and then to stay open until Wednesday right before class. And as we discussed last time, it's gonna be 3 hours like the previous exams, but I'll also add a little bit of grace time for uploading files, because you will be uploading files for this. Okay, so that's where we're at, and we're just gonna start, right? So, the last exam was mostly covered pipe flow, friction, pressure loss in 1,000 different ways. And then this exam, we kind of moved on to some sort of advanced topics about modeling flow. And we started talking about some math tools, including the Eulerian versus Lagrangian view. So what's Eulerian versus Lagrangian, someone?
So Eulerian is viewing, I think, fluid from like the fluid particle, and then Lagrangian is viewing it from like as a whole, or maybe the other way.
It is the other way around, but you remembered the distinction, but it's the other way around. So
is there like a mnemonic device that we can use to remember which one's which?
Let me see. Eulerian.
Does anyone have any ideas for that?
Well, I guess Eul kind of is like whole, and fluid particle, and Lagrangian is, I don't know. If anyone comes up with something, let me know, and I will use it forevermore.
For Lagrangian, you follow a particle along a line or through the system, and
just
so
through the system as it's moving around.
They both start with that.
Yep. So Eulerian would be like if you were looking at some kind of field, right? Like you just look at how the properties change over a field. And then Lagrangian, it's like a fluid particle, a fluid mass, and you just sort of follow it around. Okay. And so related to that, we learned about the material derivative. And so if you have a Eulerian description of a system, so you have a velocity field and a field of some other property, then you can get the Lagrangian view of how that property changes for a fluid particle as it moves across the field, right? And so, and the material derivative, which we use big D for that. Okay, like so, where if you will recall, so know how to do a dot product. So this is a velocity vector. And this is the gradient of whatever property field we're talking about. So, which a reminder about gradients, that's df dxi plus df dy j plus df dk. Cool. And just the only thing there is it's actually pretty straightforward, but you do need to know how to take the different components of a vector and to take the derivative of each of the parts and then dot them together. So it takes a little bit of multivariable calculus, but it's actually quite simple. Lagrangian as in grain for like a particle. Okay, I get that. That works. Okay. So that's the material derivative. And we did an example in class, which you can find on the old lecture slides, using that for acceleration. All right, in which case F would be V. The homework did one with pressure as F, and you can find the homework key on Learning Suite. Okay, any questions about that? Moving on.
References that we're allowed to have. We used to be on like the certain amount of notes per test. How much is it for this time?
It's the same. It's the front and back page of notes, and the book. It's always been open book, but not open slideshows. So open book, front and back page of note.
I thought it's just been open note in general, not just one page.
Oh, okay, yes,
That's
it's been
correct.
open note in general. That, you are correct
Yeah, that's my
about
understanding as well.
that. Open note, but note, like just printing out all the slides does not count as notes. That's been our deal.
So our handwritten notes.
Yes, your handwritten or like handmade by yourself notes. I want you to put notes together yourself. For one thing, that's part of how you learn, is when you put the notes together yourself. So, though I have also said that you can use like Excel to calculate stuff on this exam. So that's different than before. Okay, so that's that. The next thing we talked about, yes.
Can we use Desmos?
Decimals?
Yeah.
What's decimals?
Graphing software.
It's
Oh,
like
it's
a
graphing software?
it's there's also a scientific calculator where it's kind of like Python, where you can put in variables and then write out your calculations. It makes it useful not to make mistakes.
I think so. I kind of don't like things that integrate stuff for you.
I don't know if it can.
Lame. Okay, so sounds fine to me. Okay, so moving on. Okay, next we talked about the Reynolds transport theorem, and we did not go deep into this. We sort of covered it, and it's a way of constructing material balances. And the whole idea is that, you know, the change of a property in a control volume is equal to change inside it plus transport over the surface. That's just the variant. Yeah, so that's the idea. We didn't go into depth. It's more I just sort of wanted you to see where this came from. And then we made a couple balances out of it. And the actual problems we did, what we spent the most time on and cared about, was doing first mass balances and then momentum balances. Okay, so okay, so let's talk about that. So mass balances. So mass balances are essentially dm dt is equal to m dot in minus m dot out. And we did a problem in class and a problem on the homework all about solving these problems. It should have been like other stuff you've done before, including in calculus class. So let's go past that then, because as I said, it should have been like other problems you've done before, but unless people have a question about this. Oh, do you hear my dad talking? Yeah, he's upstairs. So that is what's happening there. I have my eye on the chat. Okay, so that's what's happening with mass balances. And then momentum balances. And let's spend some more time here because this is probably not something that you have had in other classes. So momentum balances, we derived it, but then skipping ahead, we get this. Summation of the forces on the flowing fluid is equal to okay, so could someone talk? I want to make sure I can hear people.
Can you hear me?
Okay, you are. Everyone was just silent for a while. It disturbed
Is that
me.
a beta?
That is a beta. It looks a little bit like a heart, but it is a beta.
Can you remind us what beta means? Is that the
Okay.
little d over big D?
No, beta is the momentum. Well, we have used beta to mean little b over big D before. When we talked about those
Orifice
things.
calculations.
Orifice meters, yeah, orifice meters. Then we used beta to mean little d over big D. This beta is a different beta. This beta is called the momentum flux correction factor. And it's kind of, it's just like alpha, which is the kinetic energy correction factor that we've used before. Okay. And it's there because we're integrating over a v squared term and we're using the average velocity here. And so that makes the integral not quite work out. And so we just put this correction factor in here. And on the homework problems that we did, I always just gave you what beta was, but also for turbulent flow, beta is about 1. So again, similar to alpha, the kinetic energy correction factor. For turbulent flow in a round pipe, it's about 1. For a free stream, like a hose or something, it's exactly 1. So that's where it comes from. And so if, as I said on the homeworks, I gave you what beta was. If you aren't given it, then you can use 1, but I'd like you to write out assume turbulent beta equals 1. I prefer that. Beautiful. Okay. So, so you have that on that side, and on this side you have the sum of forces, all of the forces that are happening. And so let's go through just sort of a simple example of this. So let's say you just have a pipe that goes like this. Okay, so it just goes in and out. And so flow goes in here and out here like that. Okay. And therefore, we would put on one side the sum of all of the forces on there, and then on the other side, the momentum change. And so the sum of the forces and we'd split it into x and y in this case. And so the sum of the forces into x, first I'm just going to put an fx, and that's the reaction force. That's the force of the pipe on the water, which is what actually makes it change direction. Because if the pipe didn't exert a force on the water, it would just go streaming forever. Nice. Okay. And then we're also going to add, call this 1 and this 2, pressure 1 times area 1. Okay, so you need to put the pressure force right there that's pushing on it right there. And you can use You can use the gauge pressure because atmospheric pressure is pressing everywhere, and so it will cancel out, just like when we found, like on a wall. At the very beginning of class, we found pressure forces on a wall, and we almost always use gauge pressure because atmospheric pressure cancels out because it's pushing everywhere. Okay, so that's that, and then we would put it, so going out is 2, and beta dot m dot v2 then would be what that is, except it's only the x component. So what is the x velocity going out?
0.
0. So in that case, this equals 0, and we actually get that the x component of the force of this pipe on the water is just the negative of the pressure force. And then you would do y, f of y plus, and so I'm going to assume that
Nickerson?
yes?
Wouldn't you have to consider the momentum coming into the pipe?
Oh yeah, you're right. There is an x momentum coming into the pipe. You are correct there. Okay, so v2x minus beta m dot v1 x, and I'm assuming this is a constant diameter pipe. So that does not, so that equals 0 minus beta m dot v1, because this is all horizontal, and so we just end up with f of x is equal to negative p1 a1 minus beta m dot v1. Okay, and then in the y direction, again, we have f of y, the force from the pipe. Then we have pressure, and looking at this, I'm going to assume that there is a net pressure going there, and I'm going to call that minus P2A, and I called it minus because the pressure right here is going to be pushing down on this pipe section, P2A2, and then I'm going to add the weight of the water and the pipe, minus W because it's going down, beta m dot V2 y minus beta m dot v1 x, where, and in this case, what is the y component of the velocity going in?
0.
0. So we just end up with f of y is equal to p2a2 plus w plus beta m dot v2.
Is that the weight of the water or the pipe?
Both is the weight of the water in the pipe.
Okay.
You don't always include that. Sometimes you'll just ignore that weight in a problem. I would say neglecting the weight, or that is the basic procedure. And it can be more complicated than that, and it will be more complicated than that. You could have multiple things going out, just like in the homework you had a splitter where there was one stream of water going in and 2 going out. For example, you might have negative velocities. So for example, if it went out down instead of up, then you would plug in that y velocity as negative v2, for example. But that is the basic procedure.
Other question.
Yes.
If the pipe is going out at an angle and it's not vertical, then we just split the pressure into its components, right?
Yeah, that is what I would do as well. So pressure is always normal. That's something we know about pressure. That's something we learned about pressure way back in the day. So if it's coming out at like an angle like this, the pressure force is in like this, and you can split it into a vertical and horizontal component going those things. So
Dr. Nickerson, I
Yes.
have a question about, so for some of the forces in the x direction, why are we adding P1A1, but for the sum of the forces in the y direction, we're subtracting the P2A2?
Okay, because in the x, so we just said that pressure is always normal. So here is our pipe. I'm going to draw it bigger to maybe help see a little bit better. So pressure is going to be pressing in on the water in this pipe because that's how pressure works. We're getting the forces on sort of this volume that we've drawn around this pipe. And so the pressure force is going to be pressing in on it from the outside because we're getting the forces on this section. And so pressing in on it on the outside means it'll be this direction and this direction because it's pressing in. So this,
Oh, I see. And then in the x direction, it's the same direction as the flow.
Yeah, well, in the x direction, it's not necessarily same direction as flow. It's just whatever we define as positive and negative in the x and y direction. So usually in x, we say that right is positive and left is negative. And in y, we say that up is positive and down is negative.
Okay.
So it's not with or against flow. It's just left and right, up and down. We just define those as the positive directions.
Okay, thank you.
Okay. Okay, let's see. So that is momentum. And another new slide. Woo. That is momentum. And what we went on to next in our lives was differential balances. So we just did those, and those can be thought of as integral or macroscopic balances. We got them from the Reynolds transport theory that integrates, and they are macroscopic, and there's no D's anywhere. We just use m dot, right? But now, well, no D's anywhere is a stretch because there's, you get what I mean. Now we're going to do differential balances, right? And differential balances are, we do a balance on so these all come from just doing a balance on, you know, a tiny hypothetical cube of fluid, which is then shrunk down to a single point. And so what this gives us is differential equations that show how the property changes as we go around. Okay. And that's where differential balances come from. And we started with the differential mass balance, which is also known as the continuity equation. Okay, and that's going to be D rho.
Sorry. These differential mass balances are like the Lagrangian perspective, correct?
Not precisely. Not. In fact, I would say not really. These are more Eulerian. These are more Eulerian. They're about because they describe the whole flow field.
Okay.
Just at. So this isn't a mass balance as you follow a particle, like a piece of mass around. And in fact, if you think about it, I'm not sure what that would be exactly. So this is just describes the whole flow. And if you could solve it, you would have just a whole velocity field.
Dr. Nickerson?
Yes.
Is that P for pressure or a rho?
That is a rho. That is what that is. Okay, yes, that is a rho. And when I do pressure, my pressure is like this. And so my rho's are smaller and slanty. Okay, plus and that's a U, that's a V. And that right there is a mass balance. All it's saying is that the mass that comes in has to equal the mass that comes out plus the change in density. That's what it says. Okay, and so then for incompressible flow, what happens?
Density goes poof.
Density goes poof because for incompressible flow, first of all, d rho dt goes away because the density isn't changing in incompressible flow. And then also the other rows there, those are all the same because it's a constant, and so they get canceled out. And we end up with the incompressible continuity equation, which is just du dx plus d rho, not d rho, dv dy plus dw dz. So just x component, x velocity dx, y velocity dy, w velocity dz. And we learned from this, we did a couple different kinds of problems, were the kinds of problems we learned how to do. And one kind of problem, two kinds of problem. And one kind is basically has to do with the incompressibility. So you could say, for example, under what conditions is this incompressible, or is this incompressible? Is this incompressible? So I would give you a flow field, and then you would figure out if it was incompressible by seeing whether it matched this equation. Or you might say, under what conditions is it incompressible? Something like that, by seeing under what conditions it matches that equation. And the second kind is, I give you some component, you find the other one. So if I gave you U and V, you could find W from this. Find the other one. Or if it's 2D and I gave you U, you could find V from it. Those were the two kinds of problems we did here. And you can go back, you can look at the examples in the lectures and on the homework. Cool. And that is the one where you end up with integrals and you end up with f of x and f of y at the end. That's, or whatever, but that's where this shows, that's where we saw that earlier in our lives. Okay. And now, Navier-Stokes, so remember, Navier-Stokes is also a differential balance. What kind of differential balance is it?
Momentum.
Momentum. That is Navier-Stokes. Okay, and it's basically the same as those integral balances we did before. There's sort of a change of momentum on one side, and then there's forces on the other side. So it's basically like change in momentum equals pressure force plus gravity force plus viscous force. And then, of course, you do it by volume and you differentiate and whatnot. That's basically it. And we learned how to use this to find pressure fields if I give you a velocity field, you can find the pressure field. And we also learned, so again, two kinds of problems we learned. One, given velocity, find pressure. And so that's finding pressure as a function of x, y, and z, or r, z, and theta, whatever. And the other one is find velocity profile. And the biggest part of this, the one that if you can do it, the rest will be easy, is properly simplifying Navier-Stokes. So by the way, I'm going to put the both the Cartesian and the cylindrical versions of Navier-Stokes and the continuity equation on the test. It'll be at the end after the unit conversion page I always put on there, just so you can just look at that easily. Oh, here's a thing. No things like the molar mass of air. Know that. But also remember that your book has unit conversions, it has densities for water and air, things like that. Just a reminder that those are all in there. Oh, so I now remembering that I heard a few years ago someone used fluid dynamics to model the shape of a human heart. Yeah, that would be possible. You should be able to use fluid dynamics to figure out what shape the heart has to be, because the heart is a pump, remember? So the heart is a pump, it increases the pressure of the blood, that's how it works. And it does it by squeezing it, that increases the pressure, which then moves blood through the body. And so you could use fluid dynamics to figure out what shape it has to be in order to do that. Okay, but simplifying Navier-Stokes. A few things. So these are words to look out for. Steady. Okay, steady slash, let's see, 1D or 2D. Constant pressure. Negligible gravity. Laminar flow. Those are all a third type of problem that was solvable by hand for Navier-Stokes. I don't remember, but if y'all remember, you can ask me about it. Oh yeah, the boundary layer problems. Okay, we're gonna get to the boundary layer problems. The boundary layer problems aren't exactly solvable either, but they represent a simplification of Navier-Stokes to something that's easier to solve numerically. So, well, so it is solvable by hand, but it's not explicitly solvable or exactly solvable. It's solvable numerically. We'll get to that. So these are all words to look for when simplifying Navier-Stokes equations. Also remember that anytime we have, and the reason laminar is important precisely, is that in laminar flow, the flow is in nice, neat layers, all going in the same direction. And so that allows us to simplify a lot because, so for example, if this was X going this way and Y going this way and Z going this way, for example, then we could say that, you know, Vx is equal to something, Vy is equal to 0, Vz is equal to 0, and then we could say dvx dy is equal to something because the velocity profile changes over something, but dvz dz is equal to 0. And then if it's fully developed, then that means that dvx or dvx dx is also equal to 0. So those are words to watch out for, or if you have to make an assumption in order to find the velocity profile, this is what you would write. You would like assume fully developed, for example, and then you would cancel out all dvx dx. That is the most important part, is properly simplifying this, and then you just integrate and add boundary conditions. So as a reminder of boundary conditions, common ones are at a surface, fluid velocity equals surface velocity. Okay. That's a common one. At middle of a pipe, d dx d or du dr is equal to 0, like because that's the maximum velocity. So anywhere where there's a max velocity, the derivative of 0. One we actually didn't talk about, but I'm just gonna say it so that you know it. Like at a free surface, so liquid next to air, so like if on the top of a river, shear stress is equal to 0. So, you know, just d u d z or y or whatever would be 0. Okay, so you gotta apply your bound. So simplify, integrate, apply your boundary conditions. Also pay attention to whether there's a pressure gradient or not, or whether that pressure gradient is a constant. If the change in pressure over length is a constant, then you can treat it as a constant when you're integrating. Whereas if pressure is a constant, there's no pressure gradient. Constant, 0. All right, beautiful. And there's, so we did an example in class. I posted entirely another example. I'm pretty sure we have, well, we did another example in the next class, I think, because we had a little bit of time. The practice exam has an example of doing this. So there we go. And then how much? We have about 12 minutes. I think we will get through. Okay, so that was Navier-Stokes. Next, we talked about boundary layers. Boundary layers. And so what is a boundary layer? Like, what do we mean? What's the definition of it?
Isn't it just like whatever we decide is going to be the edge of our system?
Not, okay. So the word boundary comes up in both of these things, but boundary layer doesn't mean that precisely. So any system we have, we say this is the edge, that's the boundary. And so if you know like the velocity or the pressure over at that boundary, that's the boundary condition, right? But the boundary layer, when we say that in fluid mechanics, we mean something specific. What we mean is the area around a solid surface where viscous effects, like viscous forces, are significant. That's what we mean. Okay, so we know that those viscous forces, basically the surface drags on the fluid and vice versa. That's where friction comes from. And we know that those viscous forces get less and less significant. They become much smaller the farther away you get from the solid surface. That's why when we do Bernoulli's equation, you don't have to add in friction or anything if you do your points sufficiently far away from a surface. And so that's what the boundary layer is. It is sort of this viscous area of flow around a solid surface. And so it's not just a boundary in general. That is what it means. And what is nice about this is that you can simplify Navier-Stokes in those conditions, okay? And you get the boundary layer equations, which we learned about, but we didn't really use them to do anything, but we didn't really use these to do problems, but I will write them here anyway. So you can sort of see, because we did talk about where they come from, and it's something I'd like you to know where they came from. So, So sort of what I would like you to know about this is I want you to know that this comes from a simplification of Navier-Stokes and the continuity equation that works in boundary layers, which allows something that can be solved numerically easier, which is how we get to what's called the Blausius solution for boundary layer over a flat plate. So if you have a flat plate and then you have a flow over it, then it kind of looks like this. So here's our flat plate, and the boundary layer looks like this, like it starts at 0 and then it gets bigger and bigger as it goes along. At some point it flips into turbulent and becomes turbulent. So it's laminar, and then it's turbulent, and then it gets thicker as we go along. Like that. And we have an equation for the thickness of the boundary layer that looks like this. Where this is the boundary layer thickness. And this Reynolds number is not, it doesn't have a diameter or anything. It uses X as its length dimension instead of a diameter, which makes sense because we don't really have a diameter. We're talking about over a flat plate there. And the only problem we had to do for homework just had to do with this boundary layer thickness. But I do want you to know some things conceptually. I want you to know that, again, the boundary layer is where viscous forces are significant, that it's around a surface, that it gets thicker as you go along the surface, and that one of the reasons we pay attention to this is because you can simplify Navier-Stokes. I want you to know all those conceptual things. So that was boundary layers. And after that,
we have a question about the boundary layer. With the Reynolds X is equal to rho. Is that velocity?
That is velocity. That is velocity. And what it is velocity of the flow outside the boundary layer, because basically inside the boundary layer, the velocity goes from 0 at the surface to the velocity of the flow outside the boundary layer. So you have like air at 20 miles per hour or whatever is flowing over this, and so we know that inside the boundary layer, the velocity of the air has to go from 0 to 20 in a relatively short time. There's kind of a big acceleration, and that's part of the reason there are viscous forces here, and the part of the reason it works like this. So that's what that is. That's the velocity of sort of the overall flow over the surface.
Thank you.
Cool. All right. We talked about computational fluid dynamics, or CFD. And this is another thing I mostly just want you to be able to talk about conceptually. So CFD, what it numerically solves equations. What equations does it solve?
Navier-Stokes.
Navier-Stokes, and one more, because it needs another one. If it's going to model x, y, z velocity plus pressure, it needs a continuity equation. Yep, there's 4 unknowns, x, y, z velocity and pressure. It needs 4 equations. So it has x, y, z components of Navier-Stokes plus the continuity equation. Other things, you need a grid. Which is more computationally expensive, a fine grid or a coarse grid?
A fine grid.
Finer is equal to more computationally expensive. And then we talked, so why is CFD harder for turbulent flow than laminar flow?
You need a much smaller, finer grid.
Yep, you need a smaller grid in order to capture all the little swirly cues. Other things. I'd like you to be able to, give just an explanation for what CFD is useful for. I'd like you to be able to say that if someone asks you what's CFD useful for, I'd like you to be able to tell them.
Isn't it just anything where we want to model fluid flow?
Yeah, basically. But going a little bit deeper, you can say things like, well, what can we calculate for modeling fluid flow? Well, we can predict the pressure. That's something we might care about. You can predict shear stress, right? And it's nice for anything where it's hard to do experiments, or
like
where
the surgical thing you were telling us about.
Yeah, like the surgical thing I was telling you about. Specifically, they can take a scan of your body and then get a model of your specific blood vessels, and then in the computer model, they can do the surgery and then see what happens with CFD. And that's something where you can't really do an experiment because, once you've snipped your blood vessels, they're snipped forever. But it can also supplement experiments. Anytime you sort of want to get a theoretical look at what's happening and what's flowing around, CFD can be useful and fun. Okay. Computational fluid dynamics, and then the last 2 days are all about compressible flow, because we have done incompressible flow our whole lives at this point. And now we're talking about compressible flow. Density changes significantly, which usually means some variant of a large pressure change. And we basically never consider liquids compressible because their density change with pressure is much smaller. And so it is pretty much always gases. And some situations where that might happen, long gas pipelines, pneumatic transfer. What's pneumatic transport or pneumatic conveyance?
Banked things.
Well, we talked about like powders. The homework had sugar, any kind of powder, sawdust stuff. And it uses just really highly pressurized air. Oh, bank things. Yes, bank things. It uses highly
Chicken
pressurized
scooper.
air to move it around. Chickens. Live chickens. It uses highly pressurized air to move stuff around. So that also, in order for that to work, there kind of has to be a big pressure difference. So it's going to be compressible. And then we also talked about high speed flows. Flows, Mach number greater than about 0.3. And on our first day of class, we talked about sort of isothermal compressible pipe flow. And we learned that the pressure drop due to friction is different for if it's compressible. We learned this equation here. And we also learned that you have to make, in order to get mass flow rate, you have to make sure you know the pressure, because for an ideal gas, rho is equal to MP over RT, which means that M dot is equal to rho or MP over RT times V dot, MP over RT times VA, like that. We learned about that, so we learned that if you're trying to get the mass flow rate in compressible flow, you need to know what the pressure is and the velocity or the volumetric flow rate, right? Because it'll be changing with that. We also talked about what this means. So if you're going along a constant diameter pipe and it's compressible flow, what will happen to velocity?
It will increase.
It will increase, and the reason why is because pressure will decrease just from friction. And so what happens to density?
It also
decreases, and so velocity increases in order to keep mass flow rate constant, conservation of mass.
For the P that we use in the MP over RT, if the pressure is changing along the pipe, like for the homework today, how do we have to do like a differential equation for that?
Well, that homework only asks you, it's at a specific point. So it's the P at that point. So if you have a velocity or a volumetric flow rate, the homework that was due today had 2 questions. And the first one, you're given a volumetric flow rate. And so you use the P at the point where that volumetric flow rate was measured, because it's going to move all through the pipe. So both of those things are going to change the pipe. So the important thing is you got to use the P at that point. And then the second question, you can figure out what the pressure is at one end of the pipe and at the other end, and then it asks you other questions. And so then you just have to use, you know, the velocity at that point where that pressure is. So those questions all asked you, they were all written, so you were just being asked about the velocity at a specific point where you should be able to calculate the pressure, not the velocity across the whole thing or the pressure across the whole thing.
Yeah, that makes sense.
Okay. And then finally, last of all, we are 4 minutes after, but let's finish this out. We talked about high speed compressible flow. We talked a little bit about shock waves, and I'd like you to be able to explain, just like in a couple sentences, what causes a shock wave. Especially from wave when breaking the sound barrier, or what causes a sonic boom. fact, does someone want to explain to me in like a sentence what causes a sonic boom?
The sound waves start to overlap and then they create a boundary that hits you.
Basically, the sound waves start to overlap because now they're, you keep creating new ones at the speed of sound. They bunch up. It causes really big pressure fluctuations. And what we talked about a bit more was we talked about choked flow. So what's choked flow?
That's the point that we can ensure that the fluid is traveling at the speed of sound.
So at the speed of sound, essentially what that means is that for compressible flow, you get to a max velocity, or you can accelerate to the speed of sound and then you can't speed anymore. So for example, a nozzle like this has a max velocity out of the speed of sound. So a nozzle like this is speeding up velocity, and then its maximum out is the speed of sound. And the same thing, like we just learned that through a straight pipe in compressible flow, it will speed up. It won't speed up past the speed of sound. And so what can you do to get past the speed of sound? Or supersonic acceleration or supersonic nozzles, then what do those look like?
You widen the end.
They look wider. So we learned that essentially it starts working the opposite of what it does in normal life. Once you get supersonic, it's a nozzle like this that speeds flow up, and a nozzle like this will speed it down. So if you're at subsonic speeds and you're trying to get faster, eventually you're going to get choked flow, where it reaches a maximum speed, which for a nozzle like that will be the speed of sound. And for a straight pipe, it's mostly the speed of sound. It might be a little bit lower. And then after that, in order to speed it up further, you have to put in a supersonic nozzle.
So so typically we don't do liquids through this. We just do gases because we're assuming liquids are incompressible.
Yep, because liquids pretty much all incompressible. That's why in the homework I had you calculate the speed of sound, or how fast you'd have to be going to get to Mach 0.3 in water. The speed of sound is just a whole lot faster in liquids, and so they just don't act compressible. And also we just know that gases are going to have bigger density changes with pressure, because that's what a gas is. So liquids we just treat as incompressible. All right, that is what we have. It's 2 minutes to the end of the hour. 2 minutes, my office hours will start up. Do I have any 2-minute questions?
Quick question.
Okay, yeah.
When is the test due? Because on Learning Suite it says April 13th.
I will change that. It is due Wednesday at 1 o'clock when our class is. It'll be due then, and we'll go over it in class.
Dr. Nickerson,
yes.
Will you post the homework keys for the last few homeworks that we've done?
Okay. All right. I guess let's see. It looks like I have the first few homeworks from this, keys from this section, but not the others. So yeah, I'll do that. They will go up across the rest of the afternoon, and the night I will, I'll have them posted by tomorrow morning, which is also when the exam will be open, though you don't have to take it until Wednesday, and I bet you probably won't. Have a good Easter, everyone.
Dr. Nickerson?
Yes.
Do you have class on Monday?
On Monday, no class on Monday. It's just like when we did tests before. We cancel that class, so you have that time to take it if you want. Cool.
And I don't know if you said this already, but are you going to post these review notes?
Yeah, I will post the review notes, plus I've been recording this and I'll post the video. I will get homework keys up. Like I said to Olivia, the practice exam is posted and the key is like half finished. So I'll finish it and post it. And that is what we will have. All
Thanks,
right.
Dr. Nickerson.
Thank you all very much. Lovely, lovely, lovely. Happy Easter.
Thank you.
Thank you. Good
Bye.
times. Bye-bye.